Hi, everyone. Thanks for showing up to the talk. Titan has been around for some 6 years, more or less, depending on how you count, whether depending on which founder you ask, right? Really, what we focus on are 3 lines of business. One is the cell inspection side. This is what we're going to talk about. This is during the cell manufacturing domain. One is the smart cell. This is where we're miniaturizing our ultrasound technology to be able to be instrumented onto the cells so that you can actually embed it into your applications. So this goes for electric vehicles, for energy storage systems, and consumer electronics. I will not be talking about that today. Also, the last one is about the reuse or repurposing of electric vehicle batteries for their second life. So we've received a couple of DOE awards so far, but I think the most exciting part is always when you deploy at a customer site, and that's where the true recognition of the hard work comes in. In terms of today, where we stand is we can scan about 1,000 cells per day. This is a standard EV format, EV dimension. So think of an LG chem cell, like a 30 centimeters by 10 centimeters. So we can do just under 1,000 scans per day. It's at line, so not in line, but what it allows our customers is to start learning and gaining confidence in the use of ultrasound as a really effective tool in identifying anomalies inside the cells during various stages of the manufacturing process. So we focused on high speed, we focused on high resolution. So just think of it as 200 pixels per square centimeter, right? So a lot of resolution to give us that visibility into small anomalies, and that's paired with the high sensitivity of the transducers and the electronics and the approach that we have to give us something quite superior to conventional methods of electrical sensing. And we would like this to be something that augments conventional methods rather than replace it, because we see a lot more that is not obvious when you do electrical inference. Where we're going is a fully automated handling of the cells to allow us to do 10,000 scans per day, and then integration into the production line that can reach about 80,000 scans per day. So the idea is that this is something that we can do inline for every single cell. You're not taking samples out, you're actually you're interrogating every cell, and so you're learning for every individual case, and as process changes, which it always does, you're able to catch it as early on as possible and do something about it. So in terms of the anomalies, I mean, we can see many things inside the cells, like lithium plating, tears, residual gas, the things that you sometimes wish you can see, we're actually being able to detect it. Separator wrinkling, debris, things along those lines. Basically, we're seeing changes in the properties inside the cells. So think of it as we're looking at the morphology of what's inside that cell throughout the entire surface area. In terms of the manufacturing challenges, so most of you know this better than us, but really the industry strives to achieve these perfect clones, right? You're under pressure to get high volume, high quality, and low cost, right? It's this expectation that you can manufacture perfectly homogeneous cells one after the other. But we all understand that this is a very difficult thing to achieve because of various factors, right? Low overall equipment effectiveness. This is something that outside of the battery industry is expected to be a relatively high number, while we're seeing in battery manufacturing that what you get is maybe 88% at best after 5 years of tinkering, and you then realize that by that time you're changing a lot about your processes, like chemistry and new battery formats and so on. So it's a really hard game to keep up with. And then low profit margins. It's just the pressures of producing a lower cost product so that it can be released into EV market and so on. Often, this is really related to the high cost of scrap, which is tied to low OEE. And so when you realize that 75% of the cost is in the material cost, every scrap is a painful experience that process engineers have to live through every day. Also, there is a high cost of warranty recalls. This is a real problem. It's not always about a fire, but it does lead to unexpected degradation or capacity fade and so on, which we're able to see through seeing anomalies. We're able to really have a better understanding of what could cause that earlier capacity fade than expected. So you can actually do something about that. A little bit around the advantages of ultrasound over electrical interference. Well, first of all, due to the physical limitation of this, of working with this enclosed product, you're actually constrained mostly to use electrical inference to take the best guess of what's going on inside. And that is fine, but this leads to some things like interpretations of self-discharge infers micro shorts. Capacity test infers a lack of wetting. Well, actually, it could be delamination that's causing it, or DCIR and so on. Basically, you've got these generalized results, which are good. It's the best we can. But what we're finding is that we could actually see what is causing that, and that allows you to do something more actionable with it. So advantages of ultrasound is that we can have a direct defect detection. This is something that we see the morphology inside the cell, and then we can actually determine what's that direct impact on the performance. So for example, non-uniform electrode properties, insufficient electrolyte dispersion, so you have your soaking stage, but this will work its way through to inactive zones down the line and so on and on. There's residual gas. I mentioned these things already. So in terms of localizing anomalies, we're able to understand where the issue has occurred, and that helps you understand better of what might have caused it and so on. We are able to say, okay, capacity and, for example, internal resistance may be due to delamination, and we not just, hey, this is a high DCIR result. Also, we're able to see the impact on the formation of the formation process. One of our customers actually, we showed them some of our scan results, and we told them, we're not exactly sure what this is. This part we haven't seen before. And they actually realized that it was actually their fixturing for the formation process that was having an impact on how well the cell formed in those areas. So that physical, physical pressure that was exerted without their knowledge of how they were acting upon that cell really made a significant difference. And this was great. They immediately realized, okay, we need to change this part of the process. Quick learning, it was really, really exciting for us. In terms of what this also does is, as you get the hint, right? It allows for these actionable insights. So if we can give you actionable insights, we're not going to tell you how to make a better cell. We just want to help you make a better process. Then you're able to take this and create a rapid feedback loop, so you can immediately go back to the stages that this matters. So rework becomes possible, whether that's electrolyte wetting or something else. You're able to act on it a lot sooner. You're not. Let me just clarify this. You can place our system at the end of line for end-of-line tests. You can place it before the aging process, so after the formation and degassing, and you can place it just before the formation stage, right? And so this is where you could catch defects earlier on. So you don't want to pass cells that will clearly not form well, and not to say cause a fire or something, but you don't pass this product that will definitely not be good down the line, but also you're able to create this more proactive, optimized formation where you can say these cells are good, these cells will form well, these cells are obviously scrapped, while these cells might need a more gentler formation protocol. Now, this topic itself is controversial, but it seems to be rising around and spinning a little bit. But all we are doing here is providing insights that allows the real cell engineers to do something about that and help the process engineers to. Yeah, for the sake of time, let's get to something exciting. So here's an example of cells from one production line, and you can see that there is a significant amount of variation between cells. I'm not saying that all of these cells are bad. 2/3 of these cells have failed. I mean, you got to have something interesting, right? But it does show that the way we see it, you can't easily determine from a human observing this, which cells are good, which cells are bad. But what is more important is that even the cells that are good have a significant amount of variation in them. So a lot of anomalies. Now, we don't want to create more scrap, right? We want to say, okay, these are the anomalies, and this is the impact. So you can do something more actionable. An example might be you don't want to pass, let's say, two cells that have the same electrical characteristics might have a different anomaly profile or morphology, right? That will lead to a different degradation rate. Not to say a fire or so on, but it will lead to a different degradation rate and so on. So it allows you to better grade, not just improve your process, but better grade your product for a more controlled risk profile of your warranty and so on. What I like here is that, so I've overlaid in red the cause of the failure of some of these cells that have failed. And I think it's really great when you look at the top right when it says internal resistance. It doesn't tell you anything about delamination. There's just a gross amount of delamination. It's a terrible cell, right? And then the bottom left one, low capacity. The fact that there is so much, and this is not custom made. This was a real production line. This is what happened. The separator wrinkling, I mean, this is a gross amount of separator wrinkling, but you get the point that low capacity interpretation doesn't give you enough information. And then in the rectangles are the cells that actually passed electrical tests, and I think that's great. So if you look at the middle top one, it looks quite uniform. I think that's quite nice. But you also have some that have a lot going on amongst them that have also passed. But let's take that top one in the middle that has passed the test. So here's an example of some of the views of the data that we get. And what actually happened is that as we go through these views, this is because we look at it from the frequency domain, time domain, various parameters, right? There's a lot of physics behind it. What actually happened is that we detected a tear in this cell, and it was a very obvious tear in our data. And then we confirmed it with a CT scan, and this was one example that we managed to catch a tear. And this one was almost a 2 millimeter tear that was in this cell. And this was just amazing for us, just because it was something that obviously happened to pass through. So I think you get the point that we do see things that are not obvious through the electrical means. I'll finish with a couple of more slides. Basically, here's some examples of where we could see the anomalies, and we would identify what we believe they are, and then we'd ask our customers to do a tear down so we can help confirm what we're seeing, what we're doing, and so on. And yeah, there are examples of separator wrinkling like the one before, like over here as well, anode delamination, another example of wrinkling and delamination. There's one with where you can see delamination, but also the salt deposition in that spot. But I think that during a tear down, the delamination caused it to be more of a spot where, you know. So what I want you to realize is in the ultrasound parts of these signals, how dynamic that is, how non-uniform the cells are. And that's the reality that we all live with. It doesn't mean it's bad. It's just important to know what they do to the cells. And then this slide is something that I think is really interesting, that we can see the non-uniform charge build up with the increasing state of charge of the cell. And this is something that's quite true, right? There are inactive zones, which is expected, but beyond that, we could see the areas that seem to have more of a charge buildup than the others, and that does make sense when you think about the non-uniformity in the high resistance areas, low resistance, and so on. So yeah, I think this is probably one of the most interesting ones to realize that this can be that part to replace the ambient aging of 2 weeks down to a significantly shorter time, because we can get the resolution, we can understand the morphology of that's causing that charge distribution and so on, that can lead to a lot better information earlier on in the process. So last slide. Really, so what we are trying to do here is help deliver a better product in terms of the homogeneity of the cells. We are really focusing on identifying these anomalies, knowing what's the significance of them, providing an early feedback loop to the process engineers. So 2 weeks earlier instead of waiting for the end of aging and things like that, or even before formation. I think one of the most telling quotes from one of the customers was, and I don't think he was aware that he was going to be quoted. He said, okay, of course, afterwards, but it just came out so naturally. And he said, one of the best ways to see defects in lithium batteries is through destructive means. Sure. But that the teardown from the day before has him convinced that Titan's technology is more than capable of being that non-destructive alternative. And that's fantastic. And that's what we want to do to each cell real time, as fast as the production line goes. Thank you so much.